Hey everyone, my name's Olivia. This next talk will be by Paula Vasquez, from University of South Carolina on viscoelastic models as active learning activities.
Thank you, Olivia. So, as Olivia told you, I'm going to talk a little bit about viscoelastic models and how I've been using them on my ODE class. And viscoelastic materials is my main area of research, so this is how I bring these into the classroom. But before I tell you what we're doing in there, let me first tell you what viscoelastic materials are, right? So as the name indicates, viscoelastic materials are materials that can do present both viscous and elastic behavior, right? A good example is silly putty or Play-Doh. If you heat it, if you heat it very fast, and slightly, it's going to behave like an elastic solid, like an spring. It's going to deform, but as soon as you take the deformation away or the force away, it's going to recover its original shape, right? On the other hand, if you leave silly putty overnight, it's going to behave like a viscous fluid. It's going to float out of this tub. It's going to look like honey. If you come back the next day, this is an overnight video. If you come back the next day, you turn back, the pad is not going to come back to its original one. It has no memory, just totally dissipate everything as will be a viscous fluid. So the key here with viscoelastic materials is that you can have different behaviors depending on the time scale in which you apply the deformation. And silly putty is even more special because it has a third type of behavior, and that is if you hit it hard and fast, it actually becomes a brittle solid. So how do we introduce this on a general class for ODEs? Well, we relate students to everyday materials, right? So Newtonian fluids are these viscous fluids that we all know, and they're characterized by a constant viscosity. So for example, water and honey, both of them are Newtonian. Honey will have a higher viscosity than water, right? So now we question how we can use everyday materials if they have a constant viscosity. Take, for example, hand cream, right? So you will like the hand cream while it's on your hand when you just apply to have a high viscosity, right? Because you want it to just stay there, the blob that you just put on your hand. The problem is if you try then to spread that over your skin, that's going to be hard. Just imagine if you need to spread honey all over your hands. So you say, okay, fine. I would like my hand cream to have a very low viscosity because I would like it to be very easy to spread all over my hands. The problem with this is with the low viscosity. If it's like water, it's gonna go all over the place before you even have the opportunity to spread it all over your hands. So this is where viscoelasticity becomes very obvious once you know what it is, that you use it every day. Hand cream, shampoo, paints, mayonnaise, all of these products, they're what we call a shear thinning material, right? When the shear rate, when you're not shearing it, when you're not putting any force on them, is low, then they have a high viscosity. As soon as you start shearing them, like rubbing them against your hands, then the viscosity decrease. That's why you can have both behavior. They can behave like a thick material, but once you start shearing it, it just goes easily into the hand. So that's what we call a shear thinning material. If you want to go the other way, well, this is a shear thinning. We also have what we call a shear thickening. So it's the opposite. Low shear is going to behave like a low viscosity material. High shear is going to behave like a hard material, like a thick material. So the best example of that is just cornstarch and water. And again, this is something that can be done in class. If you have, I have brought plastic cups with water and cornstarch and just plastic spoons for students to test these themselves. If you do it very slow, if you kind of stir it very slow, it's going to behave like a liquid, like any liquid. But if you try to stir it fast, it actually gets harder and harder to do. So that's what we call shear thickening. So once we recognize that these viscoelastic materials are everywhere and what are the characteristics, students now can kind of recognize that they're all over the place, right? Just about every consumer product. There's a lot of industrial applications that use these, and about 99% of any biological fluid, any fluid in your body for sure is going to have some kind of viscoelasticity, some kind of this dual behavior. So they're all over the place and they're very relatable for students, even if they don't know much about fluid mechanics themselves. Okay, so from an ODE class point of view, what is this important? Well, the fact that they can relate to everyday materials, right? And sometimes even do hands-on quote-unquote experiments in class, increased engagement of the students. I'm going to show you how real-life experiments that we do with these materials relate very well with certain functions. So it just helps students to get a physical interpretation of the ODE and their solutions. And they can relate that to a real-life problem. We're going to create models with these guys so students can go as superficial as deep as they want with this type of model. So that's an active learning quality of these. As I said, they're all over the place, so they can relate to all different applications. I'm going to show you two today. And viscoelastic materials are a very active area of research that it goes all over the place: material science, math biology, physics, chemistry. So it is connects ODEs with a lot of other fields for different students with different majors, especially in engineering. Okay, so how are we going to do this? Well, we started with what I told you in the first slide. What is a viscoelastic materials? It combines viscous, which we're going to combine it as a dashpot, with an elastic behavior, which we're going to take it as a spring. So we know from, we need the basic equations for these two elements. We know when it's spring, we're going to take a linear spring. So the stress, which is sigma, is going to be proportional to the strain, which is gamma. And the constant of proportionality is this modulus G, which is just pretty much how stiff that spring is going to be. The dashpot, in the dashpot, the stress is going to be proportional to the strain rate, to the change of the strain with respect to time. And that constant of proportionality is going to be that viscosity eta. So obviously, if we want a viscoelastic model, then the idea is that we're going to combine a viscous and an elastic element. The question is, how do we combine them? Do we combine them in parallel and series, or do we combine them in parallel? And the answer is both. And that's where the students get to explore as much as little as they want, because there's a lot of options now that you can play with these two types, with all these elements. So let's just quickly go through it. If you combine things in parallel, you're going to see that when you deform this, the strains are going to be the same for both elements because they're going to be stretched the same. And then the stresses are going to be additive. So if I want to create my constitutive equation of my model for this particular configuration, I take the stress versus strain for one element. Then for the other one, I need them to combine. They have the same strain. So I don't need gamma 1 and gamma 2. And then I just combine them because the stress are additives. And you just created your first viscoelastic model. And this model in particular is called the Voigt model. When you're in series, now the stress are the ones that are conserved and the strains are additive. So we just play the same game. We just need to add the strains since one of them has the strain rate. So I need to add both as derivatives. And now we have the second viscoelastic model, and that's the Maxwell model. So as I told you, what I've done with the students is depends on the class that I'm teaching. If it's a regular class or if it's an honors class, I'll let them go as far as they want. So once they know the rules to combine these elements on series or on parallel, they can create as many models as they wish, because now they can combine, say, a Maxwell and a spring element in parallel, or a Voigt element and a dashpot in series, and following the same two rules of stress are additive or the strains are additive, or the strains are, depending if you do it in spring and parallel and series, they can create all these viscoelastic models that I'm showing here in this column. And if you look at them, they're all quite simple. I mean, it looks complicated because we have all these constants, but keep in mind in all the etas and all the g's are constant, so they're all linear ODEs. If you work on the stress side of things, they're all first order linear ODEs, so they're usually very amenable for a basic ODE class. Okay, so mostly I focus on these four ones here for in-class activities, But if we want to go deeper, then I'll go and explore the other three. And how do I do that? Well, there is one type of experiments that we do with viscoelastic materials, and it's called a creep experiment. And what we do here is we applied a constant load and measure how the material deform under that load, right? So if I have to visualize that experiment, I put some kind of weight on my system, and then I start measuring how much the system is deforming under that way. Here is my input function, which is just a constant weight at time 0. And then at time 60, I take off the weight and I start measuring the recovery. So these are called a creep recovery experiment. And that's how that's one of the experiments we use to characterize viscoelastic materials. The good news within an ODE class, and that's the reason why I start using it, is because this input function is an impulse function, right? It's a combination of, it's a top half function, which is a combination of two heaviside functions. So I started using it in a class because I found that students get this Laplace transform section. It's a little harder for them to understand what input functions mean or when they're applied. So by kind of relating it to creep experiments, it's easier for them to appreciate what an impulse function is, and also kind of how can it be used for a real life situation. And just to bring the point home, this is not just an academic experiment in my head. People actually do this, right? That there is the measure here. We have two types of polymer systems, the PEA and PDMS. One behaves like an elastic solid, like a spring, and the other one behaves like a dashpot. And they also measured the creep recovery of some cells. I believe these were carcinogenic cells, and you can see the viscoelastic behavior of a cell. So this is something that is very much used every day on the research within viscoelastic materials. So students can relate to that, and we can find always data out there that we can use to bring to the students. So how do we do that? Well, as I said, we have, let's say, just take the dashpot, right? So the stress is proportional to the strain rate. The input is the stress because we put a constant load, and the output is going to be the strain. So if the input is this top half function and we start from equilibrium, this is my resultant differential equation. And again, if we were to show this differential equation to a student without any background or any application, these heaviside functions can be a little intimidating for them to visualize or to appreciate what it can be done. But now they can relate it to this on and off input that they put in there. And after that, you just can go and go through the whole Laplace domain and inverse Laplace to solve them. And now students can look at it and from a different perspective and be able to say, okay, this is for the dashpot, this is the viscous. So between the time where I impose the load until I take it off, between 0 and T1 is just a straight line, T. And then after that is a constant here. So it just helps students to not only solve the ODE and apply the Laplace transform, but also kind of have a visual representation of what this impulse function or piecewise continuous functions here mean physically. So one way in which I do that in class is just plain solve this for a creep flow, any of the models. Sometimes I just ask them to create themselves the models and then solve them for creep flow. Another way that I use it on class is I just give them what I call quote unquote experimental data and tell them that they should match the graphs with the models, right? So they need to solve the models and I kind of express it on this form and then try to match it. Like if you see, for example, here, the two black lines on the top and bottom plots, both of them have on the initial part, they're more or less the same, but after the recovery, the Voigt model actually goes to 0, while the fluid type model doesn't relax all the way to 0. So if they solve their equations without having any numbers, they're no fitting parameters, nothing, but just looking at the solution of the equation, they should be able to differentiate which plot belongs to a void or which plot would belong to fluid type. So that's the other one that I do in class, kind of like a mix and match plots with constitutive equations. And the last one is, this is when they want to continue working on this outside class. So we go more on the numerical side of things. And I'm just gonna, we just do a quick Jupyter notebook worksheet for them, where they just go through the same thing, where they develop the equations, they set up the system to be solved on creep experiment, and then they solve it numerically. So that's how we use this for the Laplace transform section of the ODE class. And on the last 5 minutes of the talk, there is another way in which you could use these materials on an ODE class. I don't use them because I cannot make the whole class about viscoelastic materials, and I found them they're a little better for the Laplace section. But another way we can use this, and I do it when I do like one-on-one research with students, is by working on small amplitude oscillatory shear, right? So in this case, the input is going to be the strain as a sine function, and then you just look at what is the output, the resulting stress after you make that strain. So if you have an elastic solid, you impose a sine as the input, and of course, since they're just proportional to each other, you get a sine back, and perhaps with a different magnitude because that comes from the G. But we said that for elastic materials, their input and output are in phase, or the phase angle is equal to 0. For viscous fluid, of course, if you input a sine, you're going to get back a cosine because it's the derivative of it. And in the case of viscous materials, we said they're out of phase, or the phase angle is equal to pi over 2. Viscoelastic materials are going to be anything in between 0 and pi over 2, and that's going to vary from material to material. But that phase angle is always never going to be 0 or pi over 2 exactly, and that's what it characterizes some materials over the other ones. So how is this relevant to ODEs? Well, for any of the models, let's just look at the Maxwell model here. So this is my constitutive equation, and I know the input is the strain, so all this becomes just G cosine of omega t, and this is a linear ODE that can be solved with integrating factors. And if you notice here on this side, all the constitutive equations, they all have first derivatives on sigma. And then on the other side, they have gamma alone, first derivative, second derivative. But again, remember that gamma is a sine. So what you get for any of these models under this flow is a first order linear ODE with sines or cosines on the right-hand side of the equation. And this can be solved by just integrating factors. So that's another application that can bring, I use it when I do research with students on the side, like outside the classroom, because it kind of helps them get confident about being able to do research within viscoelastic materials, because they kind of see, okay, I can solve this ODE myself, right? Like I did it in class and I can do it here. So it just kind of to give them a little boost on confidence that they can keep doing research on this area that is not that complicated.
Just want to let you know you have about 2 minutes left of the talk portion.
Okay, thank you. So just like on the creep, this is not something that we just made up for the classroom. This is just real materials out there. Here I'm putting data that we have worked with UNC Chapel Hill on lone mucus, and I'm showing you how one Maxwell mode doesn't fit the experimental data, but 5 Maxwell modes in parallel actually did a very good job with doing actually like patient. This is a culture mucus. But it's just kind of real life application of it. And just to conclude, what I wanted to show you is how we use viscoelastic models as activities for ODE class, especially since I appreciate circuits, but at some point when you're doing Laplace, sometimes you want to go beyond just using circuits, which are usually the example that we use for Laplace transforms. So I'm just giving you another option to use to cover the Laplace transform section of an ODE class. And I thank you for your attention.